Good morning, everyone. Welcome to today's class. Today we'll continue to talk about data management. And today we will finish session 2.3, handling numeric data. So let's see the topics in this section. So in this section, we will talk about strategies for transforming raw numeric variables into features for machine learning algorithms. Because machine learning algorithms usually are quite complicated and it's really difficult to converge. So they really like kind of like restricted values, values that are scaled and processed so that values are within a certain range, or the values have a certain mean or standard deviation. So basically very kind of like normalized data. Okay? So we'll talk about how to process numeric data today, and tomorrow we'll talk about how to process categorical data. So these are the topics today: rescaling features, and then generating polynomial and interaction features. So sometimes this is also useful. And then transforming features. Basically, we want to transform numeric data into continuous numeric data into discrete numeric data, sort of like ordinal data. And then how to deal with outliers. This is not exactly transform. This is not exactly discretizing data. This is another topic. So this is about using some math function to transform data. Okay? And lastly, how to handle missing values. All right, let's start from the beginning. Rescaling feature. So rescaling is very common in pre-processing task in machine learning. So many of the algorithms assume all features are on the same scale, right? Typically between 0 and 1, or -1 to 1, or they have some certain features. Okay? So we will talk about 4 scaling strategies or techniques: right? The min-max scaler, standard scaler, robust scaler, and the normalizer. So first, the min-max scaler. So this is the formula. Xi prime is the processed transformed value, and is equal to xi minus the mean of x divided by the range of x. In this formula, x is a vector. So let me make it clear. Use a different color. So this x is a vector. For example, we have n observations. Okay, this is a vector. And to min-max scale any observation in this vector. Okay? So xi prime. So you minus the mean of it and divide by max minus the mean. Okay? Basically the range. The range of it. Okay? So let's examine, study the range of the transformed data x prime. So consider 2 extreme cases. If xi is equal to the minimum of x, then what happens? Xi prime will be equal to 0, because the numerator will become 0, right? And this is one case. Another case is another extreme case. Xi is equal to maximum of x. Then you see the numerator will become max of x minus mean of x, right? Then xi prime will equal to 1. the numerator and denominator are equal. So the transformed data value xi prime will be equal to 1. So these are the two extreme values. And in normal cases, xr are in between min x and max x. So consequently, the transformed value xi prime must be in this range, okay, from 0 to 1 inclusive, right? So this is called a min-max transformer. After you transform the data, the vector, all of the values are between 0 and 1. If it's a one-dimensional data set, right, then all of the values are this range, in this range. Okay. If it is two-dimensional, then the transformed values will be within a unique square. Suppose there are two features variables, for example. Then all of the transformed values will be within this unit square. So it's quite restricted, okay, in a very small region, right? So this is a min-max. The next scalar, let's take a look at an example. So we load the Titanic data set again, right? And now we'll focus on the age variable. Age is numeric, right? Then let's use the min-max scalar to rescale the feature age. Okay, so first, load the submodule called Preprocessing from Scikit-Learn. And then we first create a scalar, or you can say we instantiate a scalar. Instantiating means create some method or object with some parameters specified. So let's create a scalar. Use the min-max scalar function and specify the range. Feature range is 0, 1. So I believe this is also the default range, but you definitely can can transform the data into different, within different ranges. For example, you can let it be between 1 and 2, or -1 to 1. Okay? You just need to change these two values. All right, so this is a scalar, right, with some parameters. Then we can call the fit transform method to transform the age column and save the result in scaled age. And then let's run it and extract the first three values in the transformed age column. Okay. So these are the three values. So they are all within the range between 0 and 1 in this interval, right? So notice that I use 2 layers of square brackets here because I want to make it a column vector. Okay, if you use single bracket, I think you will get a row vector. Anyway, this is an example of using min-max scalar to scale your data. And notice that we use fit transform, but actually there are 2 options to scale a feature. One way is to first call the fit method to calculate the min and max values of the feature, and then use the transform method to rescale the method and rescale the feature. So basically, you can do it separately, fit and transform, or directly call fit transform. Mathematically, there is no difference. However, when we talk about machine learning, you will see that we will prefer the first option. Okay? That is because usually in machine learning, before we even start training the data, we split the data to 2 parts: a training data set and a test data set. Right? So usually when we pre-process data, we will apply the fit method on the training set and calculate necessary statistics. If we use min max scalar, we will calculate the mean and max for each column, for example, and save it. And then we call the transform method to apply it on the training set, and also use the same scalar with the same min and max that are calculated from using the training set to transform the test set. That is because, remember, our model will be trained using the training set. So consequently, our test set is assumed to be in the same same population with the training set, and the model is fitted using the training set. So it will be better to use the min and max, the parameters that calculated from the training set, to scale our test set. Okay, so that the test observations are assumed to be from the same population of the training set. So at that time, it will be quite different. Right? For now, it doesn't matter, okay, because we are not there yet. We're just talking about scaling. So for now, we can just directly call fit transform. And this fit method will calculate some parameters. It really depends on the scalar or the model you are using. If you use, for example, the next scalar, the standardizer, okay, then the fit method will calculate the mean and standard deviation of each column. Okay, so it really depends on which scalar, which model we are using. The fit part will calculate some parameters, okay, statistics. Okay. And the second scalar is standardizer. So it's similar to calculating a z-score. Okay. Again, so this x bar is the mean of the column, okay, the column vector x, and s is the standard deviation of the vector. So calculated xi. So after the transformation, then the mean of x prime will be 0, right? And the standard deviation, the variance of x prime will be 1. So it's kind of like standardization process. So this is called standardizing. So let's transform age using the standard scalar. So first, let's instantiate it. I call it scalar 2. And notice that we just use default method, default parameters, and call the fit transform function method and apply it on the age column. And then we pull out the first 3 values. So notice that after we standardize the values are not bounded. However, the mean and the standard deviation are fixed. The mean is equal to 0, the standard deviation is equal to 1. But there is no lower bound and upper bound for the transformed values. Okay? So this is standardization. And then after we do that, let's test if the mean of the transformed data, standardized data, is indeed 0. If we just directly apply the mean function, you will get a missing value. So that's because, remember, age has a lot of missing values. Okay, and after you transform the data, there are still a lot of missing values. And the mean function will not ignore missing values automatically. To fix that, we can use this function instead, NaN mean. So this function will automatically ignore missing values and calculate the mean for all non-missing values. So see, the mean of the standardized age column is equal to this. Not exactly 0, but very close to 0. So this is negative 1.88 times 10 to the negative 17. So this means 10 to the negative 17. Okay, so 1.88 times. So it's very close to 0. Okay? So it's not exactly 0 because it is due to some rounding error in the calculation process. Okay? So in concept, after we standardize the data, the mean of the column should be 0. Okay? We can also verify that the standard deviation is 1. Standard deviation is good. It's exactly 1. So this is the second scalar, standard scalar. So what's the difference? The min max scale values are between 0 and 1, so they are bounded. So basically, after you use the min max scalar to process your data, the mean and the max of each column are fixed. Okay, mean is 0, max is 1. Right, so two statistics or two parameters are fixed. And if you standardize your value, then the mean and standard deviation will be fixed. Mean is 0, standard deviation is 1. But minimum and maximum are not fixed. Okay. So standardization is more common to use for machine learning pre-processing. However, it really depends on the learning algorithm. For example, principal component analysis works better using standardization, right? PCA. So this is an unsupervised learning method. It prefers standardizing. But neural network likes min-max scale data more. Right? So it really depends on the model that will use the data. All right. Then sometimes if your data is quite normal, namely is roughly speaking symmetric, or at least is unimodel and is not severely skewed, then the mean and standard deviation are good quantities to measure the center and the spread of data, right? So if the data is relatively symmetric and not skewed, then mean and standard deviation are good measurements of the center and the spread of data. However, if your data is very skewed, then mean is highly influenced by extreme values, outliers, and also standard deviation is also, because both of them will use all of the observations in your data set, all of the values in each column. So they are highly influenced. In this case, if your data is very skewed, it's better to use robust measurements of center and the spread. The robust measure of center is the median. It will measure the true center. And the robust measure of spread will be interquartile range, which is the third quartile minus the first quartile. Right? Because quartiles are not influenced by outliers. Right? So this is the 75th percentile. This is the 25th percentile. So there is a scalar called robust scalar, the robust scalar. So instead of subtracting mean from each observation, we subtract the median from it. Right? So use the median to measure the center and divide the whole thing, the difference, by IQR, interquartile range. So this is called the robust scalar. Right? We use IQR to scale the data, use mean to center the data. Okay? So consequently, this is more robust to outliers. So if your data is not very normal, then use the robust scalar. Okay? So let's see how to run it. So we first create a scalar, call it scalar 3, robust scalar. This is also in the pre-processing submodule in Scikit-Learn. Then fit transform age. Let's pull out the first 3 rows. And it's not bounded. Okay, it's not bounded, just like the standardizer. Okay, it's not bounded, but the median should be 0. right? The median should be 0 because you see in the formula we subtract the median from each observation. Consequently, the median should be 0. Right? You see. And by the way, we should use this function NAN median because there are missing values in the processed data. Right? So this is a robust scalar. The last one is a normalizer, normalizing observations. So far, the three scalars we talked about focus on columns. And notice that it's in the fitting part. Okay, it will calculate some statistics for each column. If we use min max, we calculate min and max for each column. And for standardizer, we calculate mean and standard deviation, use them to scale the data. And for a robust scalar, we calculate the median and the interquartile range. Okay. So all of them are about a column. Okay, so it will calculate these statistics for each column individually. So focus on column, and then use these statistics to scale or process each column respectively, right? But normalizer is different because it will rescale. It will focus on rows. It will focus on rows. So it rescaled the values on individual observations to have a unit norm. So instead of focusing on columns, it will focus on rows to make sure that the norm is equal to 1 after we process the data. So what is a norm? There are different types of norms. The most commonly used one is the Euclidean norm. It's defined in this way. Square root of x1 squared plus x2 squared all the way to xn squared. So here x is a vector again. So let's clearly define it. So and the norm is the square root of sum of squares of all of the values. Right. So this is an L2 norm called L2 norm. Now how to process transform the data? It will divide each observation by its row norm, and then call it x prime. So let's try to understand the scheme and why after the transformation, the norm of each row will become 1. Let's go back to the previous slide. I created an empty slide for derivation purpose. So let's clearly define everything. Okay. X is the features matrix. Right. Suppose there are P columns. And suppose we have n observations in our data set. So this is a feature matrix, a regular feature matrix with n observations and P columns. Right? Then normalizing will focus on each row. Right? Let's calculate the transform norm. Right? So for example, x2, let's focus on the second row. x2j will be equal to x2j divided by the norm of x2, right? Where the norm of x2 is square root of x21 squared all the way to x2p squared. Yeah. All right. We do the same thing for each j. J is from 1 to p. We do the same thing for each number on the second row. Okay. Then after the transformation, let's verify that the norm of x prime, x2j primes will be equal to 1 after transformation. So x2 prime norm by definition is equal to x21 prime square plus x22 prime square all the way to x2p prime square. Okay. And x2j is defined that way, so let's calculate it. So x2j square divided by x2 norm square plus all the way to the last one is x2p prime square divided by x2. Sorry, no prime anymore. In the formula, there should not be prime. So like that. Oops, did that too. In the formula, there should not be prime. Oh yeah, it is. There is prime. Sorry. Okay. So here, there should be no prime. Yeah, there should be no prime. Anyway, sorry. So then you add all the numerators together. What we'll get? If you add the numerators together, you will get x2 prime square, right? Exactly, the definition is here. And the denominator is also x2 prime square. Oops, do that too. So it's 1. Sorry. All right. So we have proof that after transformation, the norm of each row will become 1. It will become 1. Okay, it's very clear, right? And then, for example, if you have a 2-dimensional features matrix, right? 2-dimensional features matrix. Consider the transformer data x1 square, x2, x1, x2 prime, okay, after the transformation. After transformation, okay, let's consider a particular point. Then measure the distance between the point to the origin and call it the radius, right? The radius. So by definition, is equal to x1 square, square root of x1 square plus x2 square, prime square. Okay? And we know that after the transformation, the norm is equal to 1. Okay, so this is exactly the norm of this vector, okay, or point, okay, is equal to 1. So consequently, after you normalize your data, all of the transformed observations or data points will be on a unit square. Unit circle. They might be positive or negative, but the distance, which is the norm, right, L2 norm, is always equal to 1. So if you have 2-dimensional data, after you transform the data, they will be on a unit circle. Unit circle. All right. Sorry about that. My derivation is a little bit how to say bumpy. Sorry. All right. So this is normalizing. So the key point is we are transforming data along the rows. Okay? And after the transformation, the norm of each row is 1. Right? That's it. Okay, that's the key point. Let's see how to do it. So first import the normalizer from preprocessing. Okay? So now we will create a smaller features matrix with only 2 columns. And we first create the normalizer, choose norm to be L2, which means we are using the Euclidean norm, okay? Euclidean norm, call it normalizer 2, and then directly transform the features matrix. Okay? So see, this is the transformed features. You can verify that you square the first term and square the second term and add them up, it should be equal to 1. And take square root, it should be equal to 1. Okay, you can verify it easily. And alternatively, you can use L1 norm. Okay, so L1 norm is the sum of the absolute value of each values in a vector. Okay, so to do it in Python, we can just specify this argument norm equals L1. Okay? Call it normalizer 1 and transform the features. Okay? Then after transformation, the sum of the absolute value of the values in each vector is equal to 1. So now this is very obvious. 0.5 plus 0.5 is 1. All of them are positive anyway. Originally they were positive, so that's why they are also all positive. The sum of them is always equal to 1. Okay. All right, so this is another way to normalize your data using one norm. So L1 norm is also called Manhattan norm. So this is a summary of all the rescaling strategies. Standardized scalar. So this is for, so after we standardize that, we ensure that for each feature, the mean is 0, the variance is 1. And the robust scalar works similar to the standard scalar. It ensures the statistical properties for each feature that guarantee that they are on the same scale. However, robust scalar uses a median and interquartile range inside of standard deviation. And min-max after the transformation, then the mean will be 0, the maximum is 1. And the normalizer will ensure that the norm of each row will be equal to 1. Let's take a look at this diagram, this plot, to sort of compare these 4 scalars. So this is original data, okay. 2-dimensional, x1 and x2, only 2-dimensional. And x1 is between 10 and 15 originally, and x2 is between 0 and 10. Right? So in this kind of rectangular region. Right? And we color them using 2 colors, red and blue, so that we can visualize the change of these 2 groups of observations in the transformed data set, right? So that you can have a better understanding of the effect of transformation. So standard scalar, after you standardize it minus the mean divided by standard deviation, so the data will be kind of like within a circle, right? Like a cloud. Circle cloud, right? But there is no boundary, right? There's no specific boundary. And robust is kind of similar to standard scalar, but it's more like somehow like a diamond shaped region, right? But still not bounded actually. Right? And min-max, as we have I have demonstrated, if you use min-max scalar for 2-dimensional data, after the transformation, they will be within this unit square. And lastly, normalizer. After we normalize the data, all of the transformed observations will be on a unit circle. And the reason that for our data is in this region is because both x and y are positive. x1 and x2 are positive, right? So that's why after you transform them, they are also positive in this region. But they are on this unit circle. All right. Any questions? Any questions so far? Okay. The next topic is generating polynomial and interaction features. Sometimes, for example, if you fit a regression model, you have some feature variables, and you suspect that there is a kind of nonlinear relationship between some variables and y, then you might want to add higher order terms like square, or if you think two features are related, right? There is a kind of correlation between these two variable. You want to add an interaction term. So it's very convenient to do so in using the Scikit-Learn functions. So it's just called polynomial features. So we import this function, and then we create a very small feature matrix, 2 columns, 3 rows, because this is easier to for us to observe the result. Right? We just create a very small features matrix. Then create the function, instantiate the function. So degree equals 2 means the highest order term in the polynomial will be square. And include bias equals false means I will not add a column of ones to the features matrix. Remember in regression, for example, a linear regression with 2 variables. If you allow intercept, like the bias in it, then in the data matrix, there should be a column 1 added, right? Because this is corresponding to the first coefficient, the intercept. Right? So beta 0 is essentially beta 0 times 1. So you have the option to add a column 1, but we will not, because we actually don't need it. Include bias equals false means that we will not add the column 1. So now let's see what happens. We use the polynomial interaction too. So this polynomial features function and fit transform our features matrix. You get this. Right? Initially, we have 2 columns, and after we apply the function, we have 5 columns. So this is x1, apparently, right? And the second column is the original column x2. Then the third column apparently is x1 squared, right? And then what is this? This is apparently x1 times x2. And the last one is x2 squared. So it will always follow this order. x1, x2, and then x1 squared, the interaction between x1 and x2 and x2 squared. Always in this order. If degree equals 3, right, you allow cubic terms, then you will have a larger matrix, features matrix. You will follow this order. First, degree 1 terms, and then degree 2 terms, then degree 3 terms. So the sum of exponent is the degree of the term. For example, x1 squared times x2, this has degree 3 because 2 plus 1 is 3. Similarly, interaction. So this is a degree 2 term because 1 plus 1 is equal to 2. So this is a very convenient way to create polynomial terms. Sometimes you don't want to add square terms. You only want to add interactions. Then you can just add this argument. Interaction only equals true. So then let's see x1 and x2 and x1, x2 will be in the result. And x1 square, x2 square will not be there anymore. Right. All right. So this is this topic. And next one is transforming features. So we can use a function transformer to transform data in your features matrix. For example, suppose we have a data set like this. So data are on very different scales, like 1, 10, and 100, 1,000, and 10,000, 100,000. So in this case, they are on very different scales. You can use apply some function on each column of the features matrix, right, by applying some function on it. So let's first import a function transformer, right, and then specify the function we want to apply on the feature matrix. Suppose that we want to take log 10 of all of the values. Then this is the instantiation of the transformer. We can call it log 10 transformer, and then transform the feature matrix. Get the result. Now they are on the same scale. Of course, you have to make sure that this transformation is legitimate. Okay, it makes sense. You cannot just randomly take a log of everything. Okay? So this is just a one way, one option for you. And alternatively, you can use the apply function in pandas. So now we have a new features matrix like this, okay? And before you apply a pandas function, you have to convert your feature matrix into a pandas data frame first, right? Because, you know, we have learned before, like different objects in Python have different methods associated with them, right? And pandas functions are only associated with pandas data frames. So similar, this is associated with pandas data frame. That's why we first use the data frame function to convert the feature matrix. This is a NumPy array by itself, convert it to a pandas data frame. Specify the column names, call it df, and then you can apply a specific function on the data frame. By default, it will apply it on each column of the data frame. So this is the result. So this is similar with the feature transformer function in Scikit-Learn. And next topic is detecting outliers. So in introductory level statistics, you probably have learned this 1.5 IQR rule. It's just one of the strategies to identify outliers. So using this rule, an outlier is defined as if it's smaller than Q1 minus 1.5 IQR or greater than Q3 plus 1.5 IQR. IQR is Q3 minus Q1. So this is just a very commonly used strategy or rule, and it is not the only rule, of course. And for example, in a box plot, usually outliers are identified in this way. If there is an outlier if you use a box plot to plot the data, the outlier will be denoted by asterisks usually, and usually the box plot will use this kind of IQR rule, okay, 1.5 IQR rule. All right, now let's create, simulate some data using make blobs, okay? And we will simulate some bivariate data. Okay. So 10 observations, 2 features, okay. Center equals 1, so only one group, a random state. Okay. And then we intentionally change 2 observations, make them very big, like make them extreme values, 10,000. So data created using functions in Scikit-Learn data sets part, like make blobs or make regression, etc. Data are very regular, should be very regular, no outliers. That's why we need to create some outliers by ourselves. And then, okay, so feature 1 is the first column, feature 2 is the second column. And remember, we have 2 outliers. So now let's create a function to identify the index of outliers. So this is just a regular function. We call it indexes of outliers of some vector. And we first calculate the first quartile and third quartile using the percentile function. Right? So this NumPy's percentile function can be used to find quartiles, right? Percentiles, 25 and 75. And then calculate the interquartile range. And then set the lower bound and upper bound. Q1 minus 1.5 IQR is the lower bound. And then Q3 plus 1.5 IQR is the upper bound. And then we will use this where function to return the index, the row index of the value that is not within this region. Okay, so if it is smaller than the lower bound or up greater than the upper bound, the lower limit, upper limit, then they are considered outlier. So this where function will return the index of those outlier values. So we first feed feature 1 to it. Feature 1 is the first column, okay? And turns out that it correctly identified outlier. Okay, remember 0, 0, feature 0, 0 is 10,000. It's indeed an outlier, right? Using our rule, but definitely an outlier. And if we feed feature 3 to it, it identifies that it's the fourth value. Okay? The index is 3. Let's see. So that's correct. Okay. For the second feature, the third value, the fourth value is an outlier. For the first feature, the first value is an outlier. So this is just this just shows you an example that you can write your own function to identify outliers or some other observations in your data set with some certain features. All right, next, handling outliers. Whenever you identify some outliers, you have different strategies. First, drop outliers. This is the easiest way, but may not be the best way. And second is mark them as outliers and include it as a feature. So basically, you create an additional variable, right? A flag variable to flag outliers. Probably a binary variable with true or false values or 1 or zeros. Right? If it is an outlier, then 1, otherwise 0. Right? And the third strategy is transform the feature to dampen the effect of the outlier. So this, you should be very cautious if you choose to use this. Right? Make sure that it is reasonable to transform the entire feature to dampen the outliers. Let's create a small data set, data frame called houses, 3 columns, price, number of bathrooms, and square feet. So apparently the last observation has outlier values, right? Square feet and number of bathrooms. So very large numbers for both variables. So first we can drop outliers. If you are sure that the observation is due to some error, then you can drop it using conditional selection. Then it's the simplest way, but may not be the best way. Yeah. And you can also mark them as outliers. Basically, you create a new column that will be used to flag outliers. For example, we can just add a new column called outlier and then compare, use this kind of condition to assign the value. If bathrooms is less than 20, then 0, which means it's not an outlier, otherwise 1. So see. So after we run this chunk, then a new variable is created at the end, which is used to flag outliers. The last one is an outlier. By doing so, when you fit a model, for example, a regression model, you can keep this observation in the data set, because the last column will help you to absorb some kind of variation in the model. Okay? So this one can help you to regularize the model somehow. Not regularize, to normalize the model a little bit. Okay? Because this is a variable, it will contribute to the fitting result. Okay? And the last one is to transform the feature to dampen the effect. For example, we can apply the natural log function on each feature of the data, on the square feet only. Call it log SF. So basically, we create a new column called log square feet. And it is a natural log of it. Then you see that the last value is not that different from the previous regular values anymore after taking natural log. Of course, if you do this, you probably need to drop the original column and only keep this one in the data set. And you have to deal with the bathrooms, the outlier value in the bathrooms column as well. So that is another story. But anyway, this one just an example. You have the option to dampen the effect of outliers by doing some transformation. So there is no hard and fast rule for handling outliers. It's really a case-by-case problem. So you first need to know what makes them an outlier. If it is due to errors, then you can drop them or use missing value NaN to replace them. And also how to handle outliers should be based on our goal for machine learning. All right. Any questions? Next is discretizing features. So basically, create discrete numeric variables using continuous numeric variables. Sometimes it's useful too. First, binarize data. So set feature values to 0 or 1 according to a threshold. Sometimes it's useful. Right? People like binary data a lot. So to do this, we can use the binarizer function in the pre-processing submodule of Scikit-Learn. So let's first create an array called age. Again, it is just for illustration purpose. We create a very small data set. And then create a binarizer. You just need to specify the threshold. For example, 20. If the threshold is 20, then after you apply the binarizer, if the value is less than or equal to 0, 20, it will yield 0. It will turn 0. If it's greater than 20, it will yield 1. So let's see. Bit transform age. So indeed, 6, 12, and 20 will be transformed to 0. Okay? Because 20 is still less than or equal to 0. It's equal to 0, 20, so it's 0. Okay? And 36 and 68 are greater than 20, so they will be transformed to 1. So this is called binarizer. We transform a numerical variable, a continuous numerical variable, to a binary integer variable, 0 and 1. Just need to pay attention to the threshold, how the threshold is defined. So great, we draw a line. This is 20, including 20, 0, 1. Okay. And then let's move on to the next topic. Sometimes you want to break up a numeric feature according to multiple thresholds. In this case, you can use NumPy's digitize function. So you just need to specify the thresholds for all of the intervals. But in this case, just to pay attention the definition. If x is less than 20, strictly less than 20, 0. Greater than or equal to 20 and less than 65, 1. Right? Otherwise, 2. So this function digitize is a NumPy function. Right? So the thresholds and how to use the threshold to cut the values is kind of different. So we have specified 2 thresholds, 20 and 65. Right? So it's somehow like this. 20, 65. Because there are 2 thresholds, we will create 3 values. By default, 0, 1, and 2. 0, 1, 2. So from 0 to 20, from 20 to 65, from 65 to infinity, 0, 1, 2. It's slightly different from the definition when we use the binarizer function. Okay. All right. Let's run this. 0, 0, 1, 1, 2. So now 20 is in the second category, second interval. So it's coded as 1 instead of 0. And 68 is in the last category. All right. Missing values. If we have missing values, if we only have like a few observations, we can choose to delete them. Right? Delete them. One way is to use this kind of syntax. Tilde np.isNone feature. So this will remove any observations with any missing values in any column. Right? So x is equals 1 means along the rows. Yeah. So, see, and then the last row will be deleted. So that's why I was kind of I was a little bit kind of slow because in NumPy x is equals 1 means row, right? And x is equals 0 means column. In pandas, they are defined in the opposite way. And in the last slide, you see, notice that we are using a NumPy function. So this x is equals 1 is corresponding to rows, right? We'll delete rows instead of columns, with rows. So we'll delete all the rows with any observation, with any missing value in any feature, any column. All right. Now, alternatively, we can use a pandas function to drop any observations with any missing values. The function is just called drop NA. Just pay attention again, this drop NA method is associated with pandas data frames only. So that's why if we want to use it, we need to convert our NumPy array, the feature matrix, into a data frame. We just call it data frame, and then apply the drop NA method. Then you see the last row is dropped. Just pay attention to this. Whenever you use this function, you need to make sure that the missing value is coded as a valid missing value. If the missing value is coded in other ways, for example, coded as an asterisk or certain numbers or something like a letter, right? Then this function won't work. It won't help you to remove those missing values as we want. All right, let's quickly move on. So most machine learning algorithms cannot handle any missing values in the target and feature arrays. So for this reason, whenever you have missing values in your data set, you cannot ignore them. You have to handle them. Right? You can delete them. You can impute missing values using some other values, some strategies. Okay? So before we decide how to handle missing values, let's try to understand different types of missing values. There are 3 types. First, missing completely at random, MCAR. So the definition is, in this case, the probability that a value is missing is independent of everything. It is completely random, purely random. Right? Let's use one example. So for example, a survey respondent rolls a die before answering a question. If she rolls a 6, then she skips that question. So there is a 1/6 chance of skip a question, and it does not depend on anything. It just depends on the result of rolling a die, a fair die, right? And it's completely random. So this is called missing completely at random. In this case, usually it's safe to just delete the observation. And the second is missing at random. The probability that the value is missing is not completely random, but depends on information captured in other features. So the probability is not random. However, the reason that it is missing, this information is captured in other features that we have already collected. Right? For example, a survey asks about gender identity and annual salary. Gender and salary are 2 variables in the features in the survey or data set. Right? And we know that women are more likely to skip the salary question because of some reason, because they are kind of they are more likely, and this totally rely on the gender identity. And fortunately, we actually collect this information, gender identity. So in this case, the missing values are called missing at random. So basically, in this case, we can use other features to capture the pattern of missingness of other variable, like salary in this case. And the last one is the worst one, missing not at random. The probability that the value is missing is not random and depends on information not captured in our features. So in the same survey, we know that salary women are more likely to skip the salary question. However, unfortunately, we didn't collect information about gender identity. So in this case, the missing values are called missing not at random. Although we know that the missingness, the probability that the values are missing, and also the values themselves depend on gender identity, we don't have information about gender identity. This is called missing not at random. So sometimes it's acceptable to delete observations if they are missing completed at random or missing at random. The first two cases, it's fine to delete them, right? But for the last case, missing not at random, we should not remove them directly, because removing these observations will introduce bias to our data set. So because they are produced by some unobserved systematic effect. So we will miss that. All right. Now let's take a look at strategies to impute missing values. So assume that we don't want to delete those observations. We're not sure what type of missing values we have. Then we can choose to use some other values to replace missing values. So this is called imputation. There are two main strategies to replace missing values. One is to use machine learning models to predict missing values using other features. Right? A commonly used one is k nearest neighbors, KNN, k nearest neighbors. So KNN use k nearest observations according to some distance metric, usually Euclidean metric, to predict the missing value. So the underlying theory is that observations that are close to each other, for example, we have observations, two-dimensional data like this, right? And for example, this data point has a missing value in some feature, right? Then because these observations are very close to this data point, right? We can assume that their other feature values, the feature values are very similar. Okay, even the value that is missing should be similar to the neighbors in a small neighborhood. Right? So this is the logic of KNN. We would learn how to fit a KNN model in module 4, supervised learning. But for now, we just use it as an imputer. Scikit-Learn has this imputer, KNN imputer. It's very convenient to use. So let's first, again, generate some data. We use make blobs to generate 1,000 observations with 2 columns. Okay? And then we scale the data, okay, using standard scaler. I save it here, standardized features. Okay? And then we save the first column, first row value. We call it true value. Right? And then replace it by a missing value. Right? So we create a data set with a missing value. Okay, when we change it to a missing value. Okay, and then let's try to use KNN imputer to impute this missing value and see what happens. Okay, and we first instantiate the imputer. Right? You need to specify how many neighbors will be used to do prediction for the missing value, and the weights by default is uniform. That means, so in this example, suppose this is the data point we want to impute value, and the neighbor is 5. Number of neighbors is 5. Then if weights equals uniform, then all of these 5 points have the same influence on the prediction of the missing value. Right? And later on, we can see other options. And then fit transform, let's see. So this is the true value, 0.873. Right? This is imputed value, 1.96. Right? So it's quite close. Right? It's quite close. We have tried our best. And notice that if we use KNN imputer, you always feed the entire features matrix into it. You see, no matter we have missing, no matter there are missing values in a column or not, we always directly feed the entire matrix into it, because this KNN imputer will try to impute each missing value in each column with other columns, the rest of columns. For example, if you have a matrix like this, right, with a lot of columns, right, and you have a missing value here, and a missing value here, right? And if you feed this entire matrix into the KNN imputer, it will impute this value, this missing value in X1, using all of these columns, right? And at the same time, it will impute this value using the rest of the features as well at the same time. Right? So it will try the best to impute your missing values, right, in any column. And as I said, by default, it will use all of the 5 neighbors in the same way, treat them equivalently. But you also have the option to let weights be distance. Then observations that are closer to the data point you want to impute value will have higher weight on the predicted value. Okay? So if your data is not very regular, right, for example, some data points are very far away, somehow far away, you want to use this argument, weight equals distance. Right? And for us, the result is slightly improved, 1.02. So previous one we have 1.09. So it's, yeah, the error is smaller actually. Right? And alternatively, we can use some column statistics to impute values. So if you use machine learning modeling, you are using other features to predict values in this particular column, right? Other features, right? But you can also choose to use column statistics in this particular column, right? So the function is called simple imputer. Use a single value. For example, let's create a new data set. Not actually the same data set. Okay? Still, we replace the first value by a missing value, right? And then we can instantiate the simple imputer using strategy equals mean, which means we will use the column mean to replace the missing value. Right? We fit and transform the features, and let's run this. Okay? So this is the true value. This is the imputed value. The performance is very good, very good. So apparently that is because we use make blobs to create the data set, the feature matrix, and the data are very regular, basically normally distributed. So the mean is actually a very good representation of the entire column. So let's calculate the mean of the original features matrix with the missing value is -6, exactly the same with the imputed value that we use to replace the missing value. So indeed, it used the mean of the non-missing values in the column. If you think the data is skewed, you can choose to use other strategies. For example, you can use median. Okay? If the data is skewed, then median is a better measure of center, right? And then we can create a new imputer and fit transform, do the imputation. And apparently for our toy data set, the performance of median imputer is worse than the mean imputer. Yeah, again, it's because the data is very normal. And we can check the median of the non-missing values, exact the same with the one that we used to impute the value. All right, that's all for today. Do you have any questions? All right. You have no questions. Tomorrow we'll continue to talk about handling categorical data. And then you will have a quiz starting at 10:30. It will be available on Canvas at 10:30. So, all right. See you guys tomorrow. Bye-bye.